All right, so last time we were together, I talked about some of the properties of water that make it particularly good and, in fact, as far as we know, necessary for life. Today I want to talk about one more really important feature, which is going to be very crucial as we go through both this course and the next course. And it's really important that you understand this concept because it is fundamental to a lot of the way the body works, and that is pH. pH, or acidity and basicity, is a feature not just of water, but of anything that contains polar protic bonds. But and polar protic bonds means polar bonds involving a hydrogen, which, remember, the nucleus of a hydrogen is just a proton. Um, but we are mostly going to think of pH in the context of things that are in a water or aqueous solution. Yes, things outside of an aqueous solution can be acids and bases, but it's never going to happen in the body. So we're going to focus on pH and acids and bases as they pertain to a water-based solution. Now, if you'll recall, water, H2O, contains two bonds. Both of them are from a hydrogen to an oxygen. And both of them are polar bonds because the oxygen is more electronegative than the hydrogens are. That means that their electron sharing is unequal. And in fact, it's very unequal. And remember something else that we talked about when we talked about hydrogen bonds was that, well, the hydrogen only has that one electron. It doesn't have a bunch of other electrons keeping it together. So if it's involved in this very unequal relationship with water, where water is getting the electrons most of the time, it's possible for the hydrogen to just go, well, I'm not having any of this. I'm not getting anything out of this relationship. The oxygen says, well, I'm not giving you back your electron because it's very electrograbby, very electronegative. And the hydrogen can just go, well, that's fine. I'm going to leave it behind. I'm just going to leave on my own. It's just a bare proton. It can do that. It can leave, and it actually has to hook up with something else. It says, I'm going to leave you, water. I'm going to leave you for someone else. But we think of it as if the proton actually just leaves and floats off and goes and does its own proton thing. Now, since the water, the oxygen at least, got to keep that electron, it now becomes negative. Since the proton left its electron behind, well, it's a proton, and protons, we know, are positive. This is an acidic reaction. And so we have the splitting of water into two things, a proton and a hydroxide ion. So "-ide", the ending "-ide", usually means that it is an anion, a negative ion, and hydroxide means that it is a negative ion with hydrogen and oxygen. And that's basically what it is. This is often going to be abbreviated OH minus. pH is a measure of acidity or basicity. And actually, generally speaking, what pH actually means is the So pH is equal to the negative log of the hydrogen ion concentration. That's what that little p means, is basically negative log of. So the pH is the negative log of the hydrogen ion concentration, the pOH. So pOH is going to be the negative log of the hydroxide ion concentration. pCat is going to equal the negative log of the concentration of cats somewhere. If you're somewhere where you have a concentration of cats, that's just what that p means. Anytime you see that little p, that just means the negative log of the concentration. I'm not going to expect you to calculate that for this course, but there's a few things that you need to know. First off, logarithmic scales are like basically exponential. That means that every step is 10 times as large as the one before it. So this isn't going to be a linear scale. Second, since we're talking about the hydrogen ion concentration, an acid is anything that tends to lose protons. So we saw how water can lose a proton. Water, by the way, can also pick up a proton. So you can have H2O, and remember that this oxygen has 8 electrons around it, right? 4 of which it's sharing with the hydrogens, but it also has 2 lone pairs. And a proton that's floating around by itself, very sad because it's left its previous water or whatever molecule it was on, can bond to that oxygen and create an ion called H3O plus, or hydronium, which looks like this. You have an oxygen with a bond to hydrogen, a bond to hydrogen, a bond to hydrogen, and 2 lone electrons at the top, and this whole thing is going to be positive because it just picked up a proton. So water can act as both an acid and a base. It can lose a proton and it can gain a proton. Being an acid means that you donate protons. You are a proton donor. You release protons into the solution. You tend to lose protons. A base is anything that will pick up stray protons. So it is often called a hydrogen ion acceptor. Water can act equally as both an acid and a base, which is why water has a neutral pH. pH is measured on a scale of basically 0 to 14. You can have some things that are below 0 and some things that are above 14, but you're never going to find them in the body. Generally speaking, the lower something is on the pH scale, the more acidic it is. A pH of 7 is a neutral pH. That means that you are equally an acid and a base, or neither. If you are less than 7, you are an acid, an acidic solution. That means that you are donating more hydrogen ions than you are absorbing. If your pH is greater than 7, then that means that you are absorbing more hydrogen ions than you are donating. And if you are in water, where you are absorbing those hydrogen ions from is water. And we know that when water gives up its hydrogen, it becomes hydroxide. So in water, the net result of putting a base in there is that you're going to suck protons off of water, and you're going to create hydroxide ions from that water. So the more acidic you are, the more hydrogen protons, hydrogen ions you have floating around. The more basic you are, the more hydroxide ions you have floating around if you are in water. And remember, all life is water-based, so usually in life you are in a water solution. So, bottom line it, acid, low pH, donates hydrogen ions. Base, high pH, absorbs hydrogen ions, and in water, it will produce hydroxide ions. To give you an example of some things that you're probably familiar with that have a pH scale that are somewhere on that pH scale, you can take a look at this picture right here, going from really, really acidic over here at a pH of like 0 or 1 to things that are really, really, really basic at a pH of 14. To give you an example, actually an interesting biological example of something that's really acidic, stomach acid. The stomach acid in your stomach is hydrochloric acid. 1 molar hydrochloric acid has a pH of 0. It's pretty acidic. Your gastric juices, so the concentration of hydrochloric acid that's actually in your stomach, will have a pH that ranges between 0.9 and 3, depending upon how much acid you're producing at the time, whether you just had a meal, what hormones you're under the influence of, etc., etc. Lemon juice is pretty acidic. It has a pH of around 2.3. Wine and vinegar are also both fairly acidic, with pHs of 2.4 to 3.5, so they're in a mid-range acidicity. Bananas and tomatoes. Bananas contain phosphoric acid, which is the acid form of phosphate. You've probably heard that bananas are rich in phosphorus, and most of that's in the form of phosphate. Tomatoes have ascorbic acid, which is vitamin C. So you probably heard that tomatoes are rich in vitamin C. Vitamin C is an acid. So bananas and tomatoes are slightly acidic with a pH of 4.7. Coffee, bread, these are a little acidic with a pH of around 5. Milk and saliva are both slightly acidic with a pH in the 6 range. Pure water, by definition, has a pH of 7. Bases are actually a lot less common in our experience. Most of the things that we deal with, both in our outside world and our inside world, are acids. Your body actually has lots of mechanisms for dealing with acids that we'll talk about next semester. It doesn't really have all that many mechanisms for dealing with bases. So if your body becomes alkali, alkali is another word for basic, because when you use the word basic, we don't know if you're talking about simple or having too much hydroxide. So we often use the term alkali in biology when we mean basic, because it's more specific. When your body becomes too alkali, it doesn't necessarily have really great mechanisms for dealing with that. So even though that's much more rare, it can also be more serious. Some things that are slightly basic. Egg whites are a little basic with a pH of around 8. Bleach is pretty basic with a pH of 9.5. Concentrated ammonia, household ammonia, has a pH of around 10 to 11. Oven cleaner and lye. These are pretty dangerous substances. You don't want to get them on you. They have a pH of around 13 and a bit. 1 molar sodium hydroxide has a pH of 14, pretty much by definition. A few things to keep in mind. 1, your body, most parts of your body, the inside of your stomach is an exception. There are a few other exceptions, but the vast majority of your body needs to remain within a pH range of something like 7.2 to maybe 7.6. And so, like, that's the range of pH that you're going to find in your body. With, again, a few exceptions. But if your body deviates much out of that range, you die. Just no questions about it. If your body gets too far out of pH alignment, you just die. Second thing to keep in mind is that we said that this was a logarithmic scale. And that means that even though we show each of these as being about the same size, each one's actually 10 times as big as the step before it, starting from 7. So if milk has a pH of 6, it's a bit above that, but let's just say milk has a pH of 6, that means that it has a little bit of hydrogen ions. If coffee has a pH of 5, that means it has 10 times as many hydrogen ions as milk. If tomatoes have a pH of 4, then that means that they have 10 times as many hydrogen ions as coffee, which is 100 times as much as milk. If lemon juice is down at 2, say, then that means that it has 100 times as much as tomatoes, which means it has 10,000 times as many hydrogen ions as milk does. So each step here is 10 times bigger than the steps before that, and the same thing happens going the other direction. Egg whites will have some hydroxide ions. Generally speaking, the fewer hydrogen ions you have, the more hydroxide ions you have, at least if something what you're talking about is in water, which bodies are. Household bleach, which is up at 9.5, would have like 15 times, a little bit more than that. But it would have, let's say that household bleach was at 9. It would have 10 times as many hydroxide ions as egg whites do. And it would have 10 times fewer hydrogen ions. Household ammonia, let's say that that was actually at an 11. Well, it would then have 100 times as many hydroxide ions as bleach, and that would be 1,000 times as many as egg whites. And remember that that's as much hydroxide, which means that it would have 1,000 times less hydrogen. So to show you what that looks like inside of some water, right? In a neutral solution, because water can act as both an acid and a base, in neutral solution you will find some hydrogen ions, not much, but some, and some hydroxide ions, because water will just split on its own sometimes, to a very little extent, but sometimes. But because water is neutral, you will have the same amount. For every hydrogen ion, you will have a hydroxide ion. There's no imbalance. In a basic solution over here, something has absorbed the hydrogen ions, and that causes a production from the water of these hydroxide ions. So now you have more hydroxide and less hydrogen. That's the sign of a basic solution. Remember, basic solution, pH greater than 7. In an acidic solution, you have something that is donating hydrogen ions. The OHs that are naturally around in water will suck up some of those hydrogens, but in general, you're going to have a lot more hydrogens floating around. So in this acidic solution, you have a lot more hydrogen ions and a lot fewer hydroxides. That's what makes it an acid. Remember, an acid has a pH lower than 7. Last important thing to keep in mind with acids and bases and pH is buffers. Remember how I said that your body is can only really stay alive within a very narrow pH range. Your body has to be between, basically 7.2 to 7. I think you can maybe live up to 7.8, but at that point you're getting really alkali. Well, your body doesn't manage that on its own, because your body, just by virtue of doing chemistry, is constantly making acids and constantly making bases as well. So if it didn't have any help, it would wildly change in pH all the time and you'd just die. So your body has very sophisticated buffer systems. A buffer is something that helps an aqueous solution, a water-based solution, resist changes in pH by basically acting like a sponge that will absorb extra hydrogen when hydrogen levels get too high, and that will release hydrogen when hydrogen levels get too low. So it basically is something that can act as both an acid and an alkali, and it's usually a mixture of both. So a good example of a buffer that is used in your body, particularly in your blood, is carbonic acid. And carbonic acid looks like this. Now, this carbonic acid is more acidic than water because, so this oxygen here is pulling electrons from this carbon. That makes this oxygen here partially negative and this carbon partially positive. Well, this carbon being partially positive means that it is going to pull electrons from that oxygen. Oxygen does not like having its electrons pulled away. When its electrons get pulled away by this now positive carbon, it yanks even harder at the electrons coming from that hydrogen. And that means that the hydrogen gets even less time with the electrons and has more motivation to just go off on its own. And hydrogen kind of gets the short end of the stick. It's at the end. It doesn't have anything else that it can take electrons from. It's the last guy in the chain. So the more you pull electrons away from the hydrogen, the more likely the hydrogen is to just go off on its own and be a proton. So that's carbonic acid. And carbonic acid is obviously an acid. But your body doesn't just contain carbonic acid. It contains a mixture of carbonic acid and bicarbonate. You've probably heard of bicarbonate as sodium bicarbonate, which is baking soda. And sodium bicarbonate is what is called the conjugate base. When an acid loses a proton, it leaves a base behind. So this bicarbonate ion that you see right here, well, it has this oxygen, and this oxygen is now electron rich. It's got an extra electron, and that means that it is now feeling generous and is quite willing to bond with a hydrogen and absorb it. So what happens here is that if you were to dump a bunch, so like let's say that we put a bunch of hydrogens into the system, right? These are all hydrogen ions. If we put a bunch of hydrogens into the system, what happens is that most of those hydrogens just get stuck on our bicarbonate, and we make more carbonic acid. Even though we're making more acid, at least those hydrogens are not now free in the solution, so that means they've been absorbed. They're no longer affecting the pH. So we end up shifting the amount of balance that we have here towards carbonic acid, but that buffers, resists the actual change in pH because we've absorbed all of these hydrogen ions. Well, what if, on the other hand, what if we make a bunch of hydroxide ions, right? We make a bunch of base and just dump that into the body over here, right? So we just dumped in a bunch of hydroxide bases. Well, what happens is that because your body, your blood specifically, has a mixture of carbonic acid and carbonate, this carbonic acid will just lose its proton. It can do that. So it just loses its proton, and then these OHs absorb that proton and become water, which of course is neutral. And then you'll end up with more bicarbonate ion. You've shifted the equilibrium the other direction. But because you have this mixture, you have things that can like very easily donate hydrogens if a bunch of hydroxide gets dumped in there, or can very easily accept hydrogens if a bunch of acid gets dumped in. And that will help your body to resist pH change. Keep it in a very narrow range. Your body has several different buffer systems. Carbonate, or bicarbonate, or the carbonic acid system, those are all pretty much the same thing, is the main buffer system that's used in your blood to keep your blood from changing pH. Inside of your cells, you use a different pH system that actually uses phosphate and phosphoric acid as the buffer, and it's called the phosphate buffer system. We will talk more extensively about this at the end of Anatomy and Physiology 2 when we're talking about body pH balances and how they're regulated, but you should realize even at this point that pH has to be kept in homeostasis, and that buffers are a part of your body's homeostatic mechanism for making sure that that when pH gets out of whack, it gets put back in to whack, or it resists getting out of whack in the first place because your body is pH buffered.